All right, so let's look at what happens to our bonds as we go from a single bond to a double bond to a triple bond. A single bond is going to be the longest of the bonds, which makes the triple bond the shortest of the bonds. The single bond is going to be the weakest overall energy of the bonds. The triple bond will be the strongest. And in both cases, the double bond is in the middle. However, that doesn't give us a complete picture of what's going on. So, we also need to look at some information on bond strengths. My single bond is 88 kilocalories per mole. These are all going to be in kilocalories per mole. My double bond is 152 kilocalories per mole. And my triple bond is 200 kilocalories per mole. So that shows us what we just talked about. The triple bond is the strongest of the bonds. However, if we look at the difference here, the difference as we go from a single bond to a double bond is only 64 kilocalories per mole. What that means is that the pi bond only gives us 64 kilocalories per mole, or a stronger bond. So overall, the pi bond is weaker than the sigma bond. Okay, so the double bond itself is stronger than a single bond, but this second bond is weaker, and that's going to be very important too, because they're going to be much easier to break. And we can do the same thing here, and we can look at the difference here is only 48 kilocalories per mole. So this third pi bond is the weakest yet. It's weaker than the previous pi bond. And weaker bonds are easier to break, and that means that there are reactions we're going to be able to do at a triple bond that we can't do at a double bond, and there will be reactions we can do at a double bond that we can't do at a single bond, because they get more reactive as those bonds get weaker. All right, we now come to another one of our areas. Remember acid-base, resonance. We've done resonance in this chapter. Electronegativity and polarity, aromaticity and sterics. Acid-base is going to be chapter 2. So resonance and electronegativity, these are both in chapter 1. So 2 of our 5 really important areas are in chapter 1 here. So electronegativity. There's only one rule that you need to know for electronegativity. One thing to remember. If you remember this one thing, you'll be able to get all the rest of electronegativity, and that's F. Fluorine is the most electronegative atom. If you can remember that, and you know where fluorine is on the periodic table, you can figure out all the rest you need to know about electronegativity. So, what that means is that as we go across the periodic table to the right, atoms become more electronegative. As we move up the periodic table towards the top, fluorine is all the way to the right, all the way to the top, atoms are more electronegative. And more electronegative elements want electrons more than other elements. What they do is they pull electrons closer in covalent bonds. So let's take an example and look at what a CF bond would look like compared to a CC bond. Okay, so a bond between two carbon atoms, the electron density is going to be perfectly shared between those two carbon atoms because they have the same electronegativity. They have the same amount that they want the electrons. However, if I try to draw that same thing, and I'll try to exaggerate this a bit for carbon and fluorine, may look something more like this, where more of the electron density is closer to the fluorine. The fluorine's more electronegative, so it's pulling electron density closer to it. More electron density near fluorine. So there's two common ways that we show this. And really what it's showing is polarity, bond polarity. And this is the electronegativity polarity part. So two different ways we can show it. One is by showing partial charges. So we can say that the fluorine has more electron density on it than is normal, and so that has a partial negative charge. The carbon has less electron density on it than would be normal, so that has a partial positive charge. Notice the use of deltas. It's a lowercase delta. Most of you are probably familiar with the uppercase delta, which is like a triangle. This is lowercase delta. It's a little circle with a little stem coming off the top. So what that means is partial negative, partial positive. So that's one way to show it. Another way to show it is to use polarity arrows. And in complex molecules, sometimes it's easier with an arrow. So here, if I have C and F, I can say that the electrons are being pulled from carbon towards fluorine. So I put the arrow towards fluorine, and we usually cross the arrow back towards where the electrons are being pulled away from. And it kind of gives the picture of a little positive charge there. So this is saying that electrons are being pulled from the carbon towards the fluorine. And so when I look at this bond, we've talked about ionic bonds before, and we've talked about covalent bonds, but this carbon-carbon is a kind of a perfect covalent bond. But this bond between carbon and fluorine is somewhere in between. It's not ionic. We don't have a full positive charge on carbon and a full negative on fluorine, but it's not quite the same as the covalent one either. So we're going to give it a new name, and this kind of bond is called a polar covalent bond. Which is saying that it's somewhere in between a covalent bond and an ionic bond.